All right, so if you're at home, we're going to record this, and this is the alpha lesson for 12.1. Check conditions for performing inference. Interpret the symbols, a confidence interval, and a test. Okay? So, first thing you have to realize is this. When you see a capital letter, that refers to the parameter. Capital letters go to the population parameter. Small case letters go to the sample statistic in this chapter. But we did linear regression. You did it before you even walked into this course. We're coming back and combining linear regression and inference. So, here's their example. They have 260 data points here where they plotted them. It's bivariate data. What have you got? Along the input is how long the eruption at Old Faithful took in a month, and the output is how long to the next one. And are they linearly related? Okay, meaning, does a long output of an eruption correlate with a long break until the next one? So we have this, the population regression line, mu sub y equals beta, capital beta sub 0, which is the intercept of the true regression line, plus capital beta sub 1, which is the slope of the true regression line, times the input. They're identifying that. Well, in order to estimate this, we're going to take a sample. And their sample was 263 eruptions in 1 month. Right? And what are you going to get? You're going to get y hat equals small case b of 0, which is the sample intercept, plus small case b of 1, which is the sample slope. You good? Do you remember? I was going to put this up here, but I want to turn this over. If you go to your calculator, and on your calculator, you do stat calc. When you do stat calc, what did you use for linear regression before you walked through the course? You did stat calc 4. You was looking at that? Yes. What did we ask you to do in the fall? Stat calc 8. Yes? What's the difference? The way you're used to doing this is you put the slope first. And the way we do it in statistics is we put the intercept first. Doesn't really matter. You're getting the same thing, it's just backwards. And you're getting the same output. The reason you put the intercept first is to prepare you for doing multiple variable regression, which is beyond the scope of the course. Okay, but it just gets you ready to move forward. But right now, for this slide, you need to understand this. Y hat certainly is the sample. You should recognize what the hat means. But what's new to you in this slide is small case letters for B go to sample statistics. And capital letters For B, go to population parameters. Now, what happened? Well, they're showing you this is the green line represents the sample line of best fit, where the blue line is the population regression line. So the green line is an estimate of the blue line, but the green line is just one estimate. Here's another one. Here's how they chose to do it. So you got 3 different green lines, which are 3 separate sample estimates of the true line, which is in blue. But the reality is you're not going to know what the true line looks like. That make sense? But there's going to be variability among the sample lines. What's going on here? The intercept goes from 44 to 39 to 24. Depending on that sample, the slope went from 10 to 12.5 to 15.7. So now they use simulation. And all of these are taking a super random sample of 15 eruptions, ready? And they got 1,000 data points there, 1,000 dots, and that's what this looks like. And the blue vertical line is the true slope. Well, appears to be approximate normal. It's centered about the blue line, which means it's unbiased. What's the variability? Ready? Sigma the true one divided by the sample size times the population, or times the sample distribution. The standard deviation of the sampling distribution. Where does it come from? It comes from those 3 inputs. You can't do it, you can't calculate without those 3 inputs. All right? Center, shape, and spread. Now, this is a little hard to see, but it kind of makes sense. So you got this line, ready? And at each input along the line, the output is normally distributed. So the normal, so for any fixed x, the y, the outputs follow normal distribution for the given standard deviation. So if I went this far to the right, my output would be normally distributed. Now, here's the conditions. And the conditions here are a little longer for regression inference, except this. They point out in the book that you can expect when you get an FRQ, if you were to get an FRQ about linear regression, they will tell you the conditions are met. Just like they did on the thing on Friday. So you're not going to have to memorize the conditions. You see if they make sense to you. We have a mnemonic here, which we're not going to go there, so I'm not worried about it. So, what do they mean? Well, let's just look at this. Look at the scatter plot to see if the pattern's roughly linear. So the one on the left, now what happened? That is the these are residuals, yes, against the line of best fit. And the residuals are randomly scattered. These are residuals over here. Instead of being about the line of best fit, it's about the x-axis. You can express the residuals either way. So here, that appears to be random. Here, there's a pattern to that. Above, 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 below, 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 above, above, above. The picture on the right, they're not randomly scattered. Okay? Doesn't meet the condition. Independent, normal just means, ready? Box plot. So again, equal standard deviations. Well, again, we're looking at residuals. So now instead of being above, above, below, below, some random scatter, we're seeing what the dimensions of that are, or what the magnitude of these are. So these all, there's no pattern to them. Where this one, the residuals were smaller, and as the input got larger, the residuals got larger. Random sample. Okay. So here's an example. Mrs. Barrett's class did a fun experiment. Do you want to do a fun experiment? Making paper helicopters? No one wants to do fun? Some people might want to even back in the building soon. So they did a fun experiment with helicopters. Randy assigned 14 helicopters to 5 drop heights. Those 5 drop heights are getting increasingly larger. Teams of students released 70 helicopters at random order. How long till it landed? You get a scatter plot, a residual plot, and histogram. So what's happening? Well, pretty clearly, it's going to hit the ground sooner if you drop it from a lower height. Yes. Not all the time. Like sometimes these will overlap for the next one over. So the residual plot is not curved, okay? SRS, no skewness. The residual plot is symmetric, okay? Again, we're not going to focus on the conditions. We're going to expect that on a question like this, we would be told the conditions are met. So, the sampling distribution of the sample slope. Compare the population, which has capital letters, versus the sample, which has small case letters. Non-biased estimator, mu. The mean of the sample slopes will equal capital B, the true parameter, because it's non-biased. The shape of the residual is approximately normal, and there's the calculation for the variability. Independent random samples, the actuation is linear, and a box plot, okay? A box plot of residuals. So we're going to pause this and just send you to 2 questions. All right, so number 5, you get independent random samples. The true relationship, the actual relationship is linear, and the residuals appear randomly scattered. 7, the blood alcohol content is the output. So you have negative 13 thousandths plus 18 thousandths per beer. The parameter is the blood alcohol content, which should be a 0. Yes, but that's from random variation. B sub 1, that's an increase of about 200ths for every beer. Then sigma, the 200ths, 204 10,000ths, is the typical variation from the predicted value. Well, it's pretty big compared to that. In the standard error of the sample slope, the typical variation in a sample regression aligned with true regression. Okay? So what you're trying to get your mind around here is, for the alpha lesson, it's more about the big picture. The big picture is combining linear regression, which you did in the fall and you did before you came into this course, with inference, which you didn't do until you got into this course. All right? So that's all for the alpha lesson, reminding you of the calendar. Beta lesson tomorrow, test on chi-square on Thursday and Friday. If you need help with the chi-square, meaning it's going to be a multiple choice test, if you have trouble making sense of the PDF about the template for the data on Friday, and you should participate in office hours, send me an email that you want to do that on Wednesday or before Wednesday or during Wednesday. We can do office hours to help you get ready for Thursday and Friday.